Here we discuss fundamental theorem of integral calculus. It has actually two forms. First we discuss the first form of fundamental theorem. And the first form of fundamental theorem is very useful because it provides a technique for finding the integral of a given function. Now, if fx is capital F of x is a function such that f dash of x is equal to f of x, small f of x, for all x in an interval ab, then this function fx is called the antiderivative of f on the interval ab. So, if capital F and small f are two functions such that f dash of x is equal to f of x, then capital F is called the antiderivative of f on ab. Using this fact, we can integrate a given function if it is Riemann integrable. So, first we discuss certain results, that is fundamental theorem of calculus, first form. Fundamental theorem of calculus, first form. Suppose E is a finite subset of closed interval AB and f comma capital F are two functions from closed interval AB to R, satisfying certain conditions. A, the function capital F is continuous on closed interval AB. Capital F is such that f dash of x is equal to f of x for all x in AB minus E, that is except at the set of points E, capital F is differentiable and its derivative is f of x. And the third condition, f belongs to RAB. Then we have integral a to b f is equal to fb minus f of a. So this is the technique of finding the definite integral a to b f in terms of the capital F, its primitive or antiderivative. So the fundamental theorem of calculus states that if E is a finite subset of closed interval AB and f capital F are two functions from AB to R such that capital F is continuous on AB and capital F is such that f dash of x is equal to small f of x for all x in AB minus E and f belongs to RAB, then integral a to b f is equal to fb minus f of a. Let us try to prove this. Proof. Here, given that E is a finite subset of AB, that means there are finite points in AB where this capital F is not differentiable, may not be differentiable, or its derivative not equal to f of x. Now for the time being, let us assume that this E has only two such points. that is at A and B, at the endpoints of A and B. So for the time being, let E equal to only 2 points A and B, where A and B are the endpoints of the interval AB. If at all, suppose E has more points in AB, then we will divide this AB into so many number of subintervals such that these points of E come at the extremes or endpoints of these subintervals, and we can proceed the same way as we do in the case of E, where E has only 2 points A and B. So this is the idea behind the proof. Now let epsilon greater than 0 be given. Using the third condition, we have F is in RAB. By hypothesis, since F belongs to RAB, by the definition of Riemann integral, there exists a delta epsilon positive such that if P is any tagged partition of closed interval AB with the norm P less than delta epsilon, we have modulus of SFP minus integral A to B F is less than epsilon. You take this in equation 1. Now it is given that the function is capital F is differentiable throughout the interval AB except at points E, that is here at A and B. Now using the mean value theorem, applied to the function capital F, because F is continuous and it is differentiable in the interval AB except at A and B. So using mean value theorem applied to F on each subinterval xi minus 1 xi, there exists ui in the open interval xi minus 1 xi such that f of xi minus f of xi minus 1 is equal to f dash of ui into xi minus xi minus 1. This is got the result of mean value theorem. That is, mean value theorem states that if there is a function g which is continuous on some interval AB and it is differentiable in the open interval AB, then there exists a point C in the open interval AB such that g dash of C is equal to GB minus GA divided by B minus A, or in other words we can write GB minus GA is equal to B minus A into G dash of C. So using that result for the function capital F on the interval xi minus 1 xi, we can find a point ui in the open interval xi minus 1 xi such that f of xi minus f of xi minus 1 is equal to f dash of ui into xi minus xi minus 1, and this is true for all I is equal to 1 to etc. n. So take this too. Now here we have n equations. For I equal to 1 to etc. we have this similar n equations. So adding all equations into, we have sigma I is equal to 1 to n f of xi minus f of xi minus 1 is equal to sigma I is equal to 1 to n f dash of ui into xi minus 1. Now the left side, since it is a telescopic sum, this is reduced to f of xm minus f of x naught is equal to sigma I is equal to 1 to n. Now by hypothesis B, we have capital F dash x is equal to small f of x for all x in the interval AB except at E. So here ui are in AB, f dash of ui you can write as small f of ui into xi minus 1. Thus f of xn is fb minus f of a is equal to sigma I is equal to 1 to n f of ui into xi minus 1. Take these 3. Now let us observe the sum on the right side of 3. Sigma is equal to 1 to n f ui into xi minus 1 is a Riemann sum where ui is the tag that is chosen in each interval xi minus 1 xi, this interval. If you had we chosen this ui as tags of the partition P, suppose, so let P be the tagged partition of closed interval AB with the tags ui in xi minus 1 xi for all I equal to 1 to etc. n. Then RHS of 1, 3, right hand side of this 3 is nothing but the Riemann sum SFP with respect to the partition P, and therefore 3 can be written as 3 is FB minus FA is equal to SFP. You take this 4. Now from 1 we have for any tagged partition P with the norm P less than delta epsilon, modulus of SFP minus integral A to BF is less than epsilon. And at the same time 4 says that this SFP is the same as FB minus F of A, and therefore using 1 and 4, using 4 in 1, we get this is FB minus F of A. Modulus of FB minus F of A, that is SFP, minus integral A to BF is less than epsilon. Since epsilon is arbitrary, we have the result integral A to BF is equal to FB minus F of A as we desired. So this is the first form of fundamental theorem. It gives a technique for evaluating the definite integral A to B F. Now let us see some examples. Suppose capital F of x is equal to 1 by 2 into x square in the interval AB. Then we know f dash x is equal to x, derivative of half x square is x for all x in open interval AB. So when we consider this fundamental theorem of calculus, we have two functions, small f and capital F, where f is equal to this x and capital F is half x square. and E, it is a null set here, it is an empty set, because at every point f dash x is x. So there is no E here, E is only an empty set. So taking E equal to the empty set using the fundamental theorem of calculus. We have integral a to b fx is equal to capital FB minus f of a. There is integral a to b small x dx is equal to capital FB. Fx is half x square. So half b square minus half a square is equal to half into b square minus a square. Similarly, you take another function, say capital G of x is equal to tan inverse x in the interval AB, in AB. Here you can see that g dash of x, the derivative of tan inverse x, is 1 by 1 plus x square. It is true for all x in AB. Clearly this g dash is continuous. G dash is continuous. So it is in RAB. G dash, that is some gx, let us take, equal to 1 by 1 plus x square is in RAB. Taking E equal to empty set using the fundamental theorem, we have integral a to b small g of x, that is integral a to b 1 by 1 plus x square dx equal to capital G b minus G a. Capital G is tan inverse, so tan inverse b minus tan inverse a. So using this fundamental theorem, we can calculate the integral a to be 1 by 1 plus x square. Now we go to the fundamental theorem of in the second form. The fundamental theorem second form. Before going to this theorem, let us have certain definition and other results. If small f belongs to RAB, then the function defined by capital F of Z is equal to integral a to Z f ft dt or f integral a to Z df for Z in open interval, closed interval AB, let it be, is called the indefinite integral. Indefinite integral of f with the base point a. Base point a. So what is indefinite integral? An integral of the form a to z f of x dx or ft dt. It is a function of z, capital F of z, is called indefinite integral. Now we will prove a a result that this indefinite integral satisfies Lipschitz condition. It's a Lipschitz function. So that is a theorem. The indefinite integral capital F of Z defined by integral a to Z f, Z belongs to AB, where capital F, small f is in RAB, is continuous on A. So this is the result B, and we will prove it is a Lipschitz function, then we will prove it is continuous. Is continuous on AB. That is, in fact, we are proving if modulus of fx is less than or equal to m, where m is the supremum, for all x in AB, then we will prove modulus of fz minus fw is less than or equal to m into modulus of z minus w for any w less than or equal to z. W z in AB. So we prove this result. That's the proof is actually this result is saying that this capital F is a Lipschitz function. A function satisfying this condition. Modulus of fx minus fy less than or equal to k into mod of x minus y. If there is such a k for all xy in the interval AB, then we say it is a Lipschitz function. So actually we are trying to prove this function is continuous after proving this result f is Lipschitz. By additivity theorem, we have the result that if f is a function which is Riemann integrable on AB and C is such that a less than C less than B, then the function is Riemann integrable on AC and also on CB, and integral a to b f you can write as integral a to cf plus integral c to b f. Using this fact, we have integral a to z f is equal to integral a to w f plus integral w to z f for any z and w such that w less than or equal to z. ZW in A. Because integral z to w to zf we can write as integral a to z f minus integral a to b f. All these results follow. So we need in this form. So we write integral a to z f is equal to integral a to b a to w f plus integral. So this is actually a and this is w, this is z, this is b. So we have integral w to z is a to z minus a to w. That is, it is written here. Integral a to z f is equal to integral a to w f plus integral w to z f. And this written as, this can be written as, this is by the definition f of z. This is f of w plus integral w to z f. By the definition of indefinite integral, f of z is integral a to z f. So integral a to z f is f z, integral a to w f is cap f w plus integral w to z f. Therefore, f z minus f w is equal to integral w to z f. You take it number, let this be number 1 and this be number 2. We are going to prove 1. So we have got the result fz minus fw equal to integral w to z f. Since given by hypothesis modulus of fx is less than or equal to m for all x in AB, we have minus m less than or equal to fx less than or equal to capital M plus m, a less than or equal to x less than or equal to b. And therefore, integrating over the interval ZW, WZ, WZ, we have minus m into z minus w is less than or equal to integral w to z f less than or equal to m into z minus w. This you take it as 3. Therefore, already we have fz minus w is integral w to z df by 2. And here we have got minus m zw is less than or equal to integral w to z df less than or equal to m into zw. So, using these 2 in 3, we get minus m into z minus w is less than or equal to fz minus fw is less than or equal to m into z minus w, using 2 by 2. And therefore, modulus of fz minus fw, modulus of fz minus fw, which is actually modulus of integral w to z df, modulus of integral w to z f is less than or equal to m into modulus of z minus w. Since whenever minus k less than or equal to some x less than or equal to k, we have mod x less than or equal to k, or mod x less than or equal to mod k. So, modulus of fz minus fw is equal to modulus of integral w to z df is less than or equal to m into modulus of z minus w. Thus, we have the result that for all set w, where w less than or equal to z, modulus of fz minus fw is less than or equal to m into modulus of z minus w. For all set w in the interval AB with the w is such that less than or equal to 0. This shows that f is a Lipschitz function. This is actually what we wanted to prove here. Whenever mod of z minus w is less than delta, we can show this is some mod of fz minus fw is some less than epsilon using this. Hence, f is Lipschitz. And every Lipschitz function is actually uniformly continuous, hence continuous. Since every Lipschitz function is uniformly continuous, f is continuous. F is continuous on the interval a. So the indefinite integral capital F defined by fz is equal to integral a to z f is actually a continuous function on the closed interval a. Now we prove the theorem, fundamental theorem. Second form. It states like this: let f in RAB, that is f is a Riemann integrable function, and assume f is continuous at C in AB, then the definite integral capital F defined by fz is equal to integral a to z f, where z in AB is differentiable and f dash of C is equal to fc. F dash of C is equal to fc. It is differentiable and its derivative is f of C. So this is what we have to prove, the second form of fundamental theorem. Proof. Let given actually C in AB is the point where small f is continuous. That is, wherever f is continuous, that is the meaning. Wherever small f is continuous, capital F is differentiable at that point. That is what this theorem is intending. Wherever small f is continuous, there capital F is differentiable and its derivative is equal to the function, value of the function at that point. Given f is continuous at C, continuous at C in AB, we take only the right continuity of f. By the definition of continuity, for a given epsilon positive, there exists a eta epsilon positive such that modulus of fx minus fc is less than epsilon for all x satisfying c less than or equal to x less than c plus eta epsilon. We are taking only the right continuity at the point C. So we need consider only the interval C plus eta epsilon, not C minus delta we are not taking, C plus delta only we are taking. So take this number 1, and this one can be written as, that is fc minus epsilon is less than fx is less than fc plus epsilon. Now let h be a number such that 0 less than h less than eta epsilon. That is, we are taking the length, h is actually the less than this interval, length of this interval. Then by additivity theorem, additivity theorem. Apply to the function small f. On the interval c plus h we have capital F of c plus h minus f of c is equal to integral c to c plus h f. F of c plus h minus fc is equal to integral a to c to c plus h f. We are taking this like this. A, this is c, and this is c plus h, this is v. So integral a to c plus h minus integral a to c is integral c to c plus h, and that is f of c plus h minus fc. This is actually integral a to c plus h f minus integral a to c f. This is f of c plus h minus f, which is equal to integral c to c plus h f by additivity theorem. Now on this interval c plus h, this condition is satisfied. It is, take it as 2. 2 is satisfied because 2 is satisfied for all x such that c less than or equal to x less than c plus eta epsilon. So since h is less than eta epsilon, for every x in the interval c plus h, this 2 is holding. Note that 2 holds for all x in the interval c plus h, and therefore integrating over the interval c plus h, we have integrating over integrating the 2 over c plus h, we have integral c to c plus h fc minus epsilon is less than integral c to c plus h fx dx is less than integral c to c plus h fc plus epsilon. If you want, you can write dx here. That is fc minus epsilon into the length of the interval h is less than or equal to integral c to c plus h fx is capital F of c plus h minus capital F of c is less than or equal to integral c to c plus h fc plus epsilon is fc plus epsilon into h, because fc plus epsilon is a constant function. So fc minus epsilon into h is less than or equal to f of c plus h minus fc less than or equal to fc plus epsilon into h. Dividing by h, fc minus epsilon is less than or equal to f of c plus h minus f of c divided by h is less than or equal to fc plus epsilon. Now subtract fc or add minus fc. Adding minus fc on both, we get minus epsilon less than or equal to f of c plus h minus f of c divided by h minus small f of c is less than or equal to epsilon. That is modulus of f of c plus h minus f of c divided by h minus f c is less than or equal to epsilon. So since epsilon is arbitrary, epsilon tends to 0 when h is tending to 0, when h tends to 0, and therefore limit h tends to 0, f of c plus h minus fc divided by h minus fc equal to 0. that is limit h tends 0 f of c plus h minus fc divided by h is equal to fc, that is the right derivative of f the function at c, that is f dash c is equal to f of c. So we got f is differentiable at c, f dash c is equal to fc on the right of the interval c. Similarly, we can prove on the left of interval c also by taking, instead of c eta plus epsilon, you take minus eta epsilon, c minus eta epsilon c. In that interval, same way if you argue, we get f is differentiable at the left end of, left point of c also, left side of c also. That is, f is right differentiable at c. Similarly, we can prove f is left differentiable at c. Differentiable at c by considering the continuity of the small f at left continuity at the point c. Hence, f dash of c is equal to f of c. So this c is the point where the small f is continuous. Wherever f is continuous, capital F is differentiable. That is this fundamental theorem. So this result can be generalized like this. If f is continuous on AB, then the indefinite integral capital F defined by f z is equal to integral a to z f where z in AB is differentiable on AB and capital F dash of x is equal to f of x for all x in AB. So this general theorem can be deducted from the fundamental theorem of the second form. Proof is very simple. By fundamental theorem, we have that if small f is continuous at c in AB, then the definite integral f is differentiable and f dash of c is equal to f of c. Since in this theorem it is given that f is continuous at every c in AB, at every x in AB, you can say like that, every x in AB, and therefore by applying the fundamental theorem we have f dash of x is equal to f of x for all x in AB.